This is for the year 10s. Triple Scientist. It's just a physics paper, Unit 1, and we're looking at 2017. Higher tier, which most people will be doing. So there's going to be 7 questions in this exam. As always, page 2 is the equation sheet, and then we'll move on to question 1, which seems to be about earthquakes. We've got this diagram. We've got 3 seismic stations, A, B, C, and they've all received an earthquake movement, and it's made a seismogram, and it tells us how far away the earthquake was from each of these seismic stations. The first question is, where is the epicenter? Where did the earthquake start at? Which is here, at the intersection. So that's going to be the first mark there. Why do we need 3 stations? Well, if we only had 2 seismic stations, say I only had A and B, they intersect there or there. There's 2 places when you have 2 stations. You need the 3rd station to get to the exact point. And then part B, explain which station detected the earthquake first. Well, that's going to be the one that's closest to the epicenter, which will be C. Let's write these answers in here. Explain why 3 seismic stations are needed. So if you have 2 stations, there will be 2 possibilities. With 3 stations, there's only 1 intersection. Move on to the next question. We've got a couple of the seismographs, and we know that station A is double the diameter. So if it's double the diameter, it's going to take twice as long to get to A than it does to get to B. And we can see that the P waves have taken 10 seconds, which means this P wave will only take 5 seconds. And likewise, to get to the S wave, it's taken 1 minute. And if that's double the diameter, this one will take half a minute. Let's transfer those times to the answer. So the arrival of the P wave is going to be 1 hour, 15 minutes, and only 5 seconds onwards from there. So it'll be 15 seconds. And then the other one will be 1:15. It'll be an extra 30 seconds on top of this. We have to explain how we arrived at our answer. So I will say we use the fact that if it was double the time or double the distance, then it's double the time. So it's double the distance to A. So the time was doubled. We use that fact to answer those questions. That's the end of question 1. Question 2. Family from Wales researched PV cells before they bought some, and they were told that they could expect that much energy. So kWh, that's energy, the amount of energy units. Yes, and this is the graph. So it's going to ask us some questions about the graph. Use the information from figure 1, the graph is figure 1, to validate the claim that they would generate 3,400 units annually. So it's adding them up. So we've got 50 plus 150 plus 250 plus April, which is 350, plus May, June, July, which is 1,500 in total, Then we're going to add August and September. Then I'll add the last three together, so it's 200, 300, 350. If we add all that up, so we've got two, I'm going to just group them together. I'll group those. So it can make 3,400. Exactly. Some data for the last 30 years show the average number of sunshine hours for each month in Wales. So I find it quite funny that there's no units on the left-hand side. Look, they're not actually saying you get that many hours of sunshine. Describe how the information from figure 2 supports the general trend shown. Well, we've got May, June and July is the highest and the same values. That's one of the bits that is it's going to back it up. What they didn't accept there is just to say you can't just say it's the same shape. That was wrong. You have to actually give some facts about the graph. Or talk about the shape, something about the shape. You can't just say same shape. The Welsh office has also had the data for the maximum, that's in bold. And they're not allowed to use this. So why can't they use that as their data if that's the maximum amount? Basically, it's misleading, isn't it? Yeah, if you expect, and if they said the maximum amount was 10 hours and you bought it thinking you're getting 10 hours, you're not going to. That would only be the maximum you get, and not all years or months are guaranteed that amount. You can't guarantee they'd get that much. Then we have another table which is showing us what we expected and what we actually get. So you can see that perhaps in September we actually got less than was expected. October was the same. For instance, March we had more sunshine hours, and in April 2016 it was more than we expected. So let's have a look at what this graph is wanting to ask us. Okay, we have to tick 3 boxes, and 3 of these are correct statements. And the correct 3 boxes is box 2, 5, and 6. Move on to question 2. In April 2016, the PV cells generated 600 units of electricity. That means they're going to produce 3 kilowatts. Now, this is a power, and this is an energy. Use an equation from page 2 to validate this claim. So we're going to be using the units equals power times time. The number of units that was made was, it's the energy units, so that's 600, equals 3 times the time. So what time are we going to use? We're looking at April 2016. Let's scroll up. April 2016 is this one. It made 200 hours. It's April 2016, so there's 200 hours there. If I put 200 hours in there, 3 times 200 is 600, which is what we expected. I validated it. I've got the right answer, or the answer we expected, by doing the maths myself. Next, the PV cells were expected to produce this much energy. However, it actually made this much, so it's more than they expected. And the family saves 29 pence for each unit that was made. So how much extra money have they saved? Well, that's an extra 270 units extra. Because they are asking for the extra money, not just the total money, the extra money. So, and if they've saved 270 units and they cost 29 pence each, 270 times 29 is 7,830 pence. And it wants the answer in pence, so I will leave it as pence. If it wanted it in pounds, I would change it to £78.30, but they wanted the pence. If the PV cells continue to generate more, so that means you're going to be saving more money than you would expect. What would that have on the payback time? Well, the more money you save in is going to have a quicker payback time. You'll get your money back in less time because you're saving more. And that's question 2. Question 3. It's a rechargeable toothbrush. We can see an iron core, secondary coils, primary coils, and transformers. So this is going to be about electromagnetism. So explain how we get a voltage in the secondary coil of the transformer. Right, that is because in the primary coil, there's an AC current. Which produces or induces an alternating voltage. And an alternating or changing magnetic field. So that changing magnetic field then cuts through, or is in the field, or the secondary coil is in the field of the changing magnetic field. The secondary coil is in the changing magnetic field, which induces a current in the secondary coil. So there's all this idea that there's a change in magnetic field produced by the first one. So if something is 100% efficient, that means there is no wasted energy at all. So nothing is wasted. All the energy that goes in comes out as useful. It doesn't waste anything at all. Part 2. So we have a secondary coil that has 480 turns. So I'm going to write this over this side. It's 480T. The primary coil has 9,200 turns, and that's got a 230 volts. So I'm making this is the primary on one side, and this is the secondary on the other side. And we want to calculate this voltage. So we're going to need to find out what happens to the number of turns to go from here to here. Well, if I divide them, so I want to find out what the multiplier is here. So if I divide them, 9,200 divided by 480, I get an answer of 19.2. So that's what's happening here. For me to get from this to this, I'm going to go that way and divide by 19.2. So I'm going to do the same here. I'm going to divide it by 19.2. 230 divided by 19.2 means that this is 11.98. So that's the voltage I'm going to get out, which is roughly 12 volts. Given that the current produced in the secondary coil is 100 milliamps, use an equation to calculate the power of the toothbrush. So we're going to use power is current times voltage. Now the current is 100 milliamps, so that's 100 times 10 to the minus 3. We're going to get rid of the milli part. And we're going to times that by the voltage. We just found out the voltage to be 12. And that goes into a calculator. It gives you an answer of 1.2. Quite nice for 3 marks. Just remember that milli, what it means. And that's on page 2 as well. On to question 4. Question 4 is asking me about the ring main circuit, just to do with the domestic electricity topic. We've got some currents here for different devices, which we may need to use. And we have a diagram showing the consumer box, an MCB, live, neutral, earth. And the first question is something we've seen many times. What is the function of the earth wire? So straight out of a book, if the live wire touches the metal casing, so that's what's going to happen to cause the fault, then the earth wire provides a low resistance path to take the current to earth. The ground. State 2 advantages of using a mini circuit breaker over a fuse. So it can be easily reset. Just got to flick the switch. And the other one is that it's faster, because it's more sensitive, which is the same reason. So one for them, one for easily reset. The cable of the ring has 21 amps passing through it. Why is it safe to use all of these appliances at the same time? Well, if we look at the 3 appliances, we have the tumble dryer, the kettle, and the toaster, 9, 10, and 5. So that's 9 and 10 and 5, which is 24 amps. But don't forget the current is working in 2 paths, some along the neutral and some along the live. So that split between the live and the neutral so each cable would only have 12 amps, which is less than the 21, which is the most it can take. Okay, 4 marks now. We're moving on to heat transfer. Heat transfer of a metal saucepan. So explain in terms of particles how it gets through the metal saucepan by conduction, and then how it heats up the water by convection. So split it up for us. So we'll talk about the conduction first of all. When the particles in the metal get heated, they vibrate more vigorously. They're colliding with their neighbouring particles. Passing the energy on. And heating up the metal. That's the conduction part, that's how we get to the metal. Now we've got to talk about the convection. So when the convection is in the water, so when those particles are heated, they get less dense and rise. That pushes the colder, more dense liquid down, setting up a convection current. So we talked about conduction, we talked about convection. Question 5. It's an electrical circuits question. We are looking at the voltage and current through a lamp. So I know this is going to be a curved line for the lamp, which it is. However, this is and a resistor, and these are the data for a resistor. I know the lamp is a curved line, but I also know a resistor is going to be a straight line. Plot the data for the resistor and draw a suitable line. There we are. So 1 is 0.20. Where is 0.20 on this? Each two little squares is going to be 5. So that would be 10, that would be 15, 20. So 20 is going to be there. And the same with the other ones. 2 and 0.40. 40 is going to be there. 4 and 0.8. 0.8 is going to be there. And the last one, 6 and 1.2. 1.2 is going to be there. And it will be a straight line, which I haven't got a tool to do a straight line, but you would use a ruler. I'm going to write ruler on there. Make sure you do it with a ruler, please. This is a straight line. Describe how the current through the lamp changes as the voltage is applied to it. So the basic answer would be more voltage increases the current, or more current. But now we have to talk about the shape of the line. It's going to have, starts off with a big increase and it gets a smaller increase here. So there's a big increase in current here and there's a smaller increase in current here. And the best way we can describe that is just to say at a decreasing rate. That's just a way of saying that it's getting smaller. The increase is getting smaller. Finally, the group connects two components in parallel. So there's the lamp, there's the resistor in parallel, with a variable voltage power supply and an ammeter. The ammeter is going to measure the current. Use a graph and an equation from page 2 to calculate the resistance of the lamp at 3 volts. So the equation we're going to use, resistance is voltage over current. We know that the voltage is 3 volts. So what current do I get from the lamp when the voltage is 3 volts? 3 volts here. Let's go up to the lamp there and across. 0.85. So my current when the voltage was 3 volts is 0.85. 3 divided by 0.85 is 3.5. Just got a resistance of 3.5. I'm going to write this in here. if this was 3 volts, the lamp is 3.5 ohms. Calculate the ammeter reading at 3 volts. So we're going to use current equals voltage divided by resistance. We know the voltage was 3 volt. I think I'm jumping ahead of myself here. Let me take rid of that. I just worked out this was 0.85 amps by using the graph. I wouldn't know what it is here, but I can add this number to whatever the current was in the resistor. So the lamp is 0.85. The resistor at 3 volts has a current of, we'll read the scale, so that would be 0.55, 0.60, that would be 0.65, so this would be 0.625. That's pretty accurate, somewhere around there. Depending on where your line is. So that number can change slightly, it depends upon your line. And then if we add those together, if this was 0.6, this here at the ammeter was then added together, which is 1.45-ish, depending on what your answer was there. Calculate the total resistance of the circuit. This is what I was going to do. So we've found out that the top one, the lamp, from our answer here is 3.5 ohms. If I do the same and find out what the resistance of this resistor is, let's do that now. So that resistor is going to be voltage divided by current. The voltage is 3, the current was 0.6. 3 divided by 0.6 is 5. And I'm doing this the hard way around. I don't need to do all this. It'll still work like that, because then I've got 2 in parallel. I might as well do it this way now. And then we'd go through that to find out what RT is. But a far easier, quicker way to do this is... It's a far easier way of doing this. I just realised, because we found out that the current is 1.45 there, haven't we? So if the current was 1.45 amps, the voltage was 3 volts, I can literally just use resistance equals voltage divided by current for the whole circuit. The voltage was 3, the current was 1.45 amps, because we just said it was there. 1 divided by 3.45 is 2.1. Far easier way. I complicate it myself sometimes. Explain in terms of current while the whole circuit has less resistance. Explain in terms of current why the whole circuit has less resistance than resistance in terms of either component. Because there's 2 paths, there's going to be more current. And the reason why there's more current is because there's less resistance. They're opposite. The voltage supply goes from 0 to 6. So how would this graph show that we have a bigger resistance? So this is a really tricky question. Right, the whole question, I mean, not just this one. So the voltage is increased from 0 to 6. Explain how the graph shows that the lamp has a bigger resistance than the resistor at 6. Well, I think we can do the maths here, can't we? If I find out the resistance is voltage divided by current of the lamp, so at 6 volts, 6 divided by, I'll get the numbers on the graph, this is annoying me. At 6 volts, the lamp is 1.125. 6 divided by 1.126 divided by 1.125. That's going to give me a resistance of 5.3. Now we'll do the resistor and do exactly the same thing. So at 6 volts, the current of the resistor is...
Goodbye, sir.
Bye. The current of the resistor is up here somewhere, 1.25. 6 divided by 1.25 is 4.8. So which one is bigger? That one's bigger. The lamp is bigger. We could have also said, by looking at the graph now, it's got more current, so it's going to have less resistance. And it would be as simple as that. Up until this point here, look, the lamp has more current, so that will have the lower resistance. So that will have a higher. And the next question here is, we're not allowed to use calculations this time. Compare the powers of the lamps. So I'm not going to do a calculation, but I'm going to make us think of this. So they've got the same voltage, but the current is going to dictate what the power is. So if I look at this graph, I kind of alluded to it earlier. Up until this point, the lamp has more power because it's got more current. But at this point here, they've both got the same power, which is about 5.3 volts. They've got the same power, and then anything bigger than 5.3, the resistor will have more power because it's got more current. So I'll write that in here. So they're going to have the same power at, what was it, 5.3 volts. If it's less than 5.3 volts, then the lamp has more power. But if it's bigger than 5.3 volts, then it's the resistor has more power. Tricky question, the whole thing was there. Number 6. 6 marker. The meaning of the word latent is hidden. And it is suggested that heat is something that is hidden. So I know it's something to do with the bonds. We've got the fusion of ice. So this is latent heat. That's where the solid turns into a liquid. And I've got another latent heat of vaporization, which is where the liquid turns into a gas. So what's the difference between the two values and in terms of behavior of molecules? Doing this, I'll start off answering this with what this latent heat means. So latent heat is the energy required to change the state of 1 kilogram of a substance. The fusion, the latent heat of fusion is from solid to a liquid. Something I'm going to add here, I forgot. So it's without changing temperature. So let's go back to this bit. So the latent heat of fusion is from a solid to a liquid. The energy is used to break the bonds. Which is the same as the latent heat of vaporization. It's from a liquid to a gas. But which one number is the biggest? The bigger one is the vaporization. Look, it's 2.26 million. But you need more energy is needed as more bonds are broken in this stage or in this change. Question B. So this is asking us to apply our knowledge of the latent heat, and it looks like specific heat capacity. So we've got 500 kilograms of aluminium, and we have to melt it from this to be completely melted at that temperature. So first of all, we have to heat it from 20 degrees Celsius up to 660 degrees Celsius, and then it's going to stay at 660 degrees Celsius while it's melting. So here we're going to be looking at specific heat capacity to heat it up, and at this point here we're going to be looking at our latent heat equations. And afterwards I will see if it can be done in the time of 1 hour. But first of all, we need to know how much energy we need to do this. So the energy for the specific heat capacity bit is MC delta T. We have 500 kilograms of aluminium. The specific heat capacity is 900, and I want to heat it 640 degrees is the change. If I put that into a calculator, I'm going to have an answer of 500 times 660 times 900, 200. So many joules I need. That. I made a mistake there when I typed in a calculator. 288. So that was just to heat it up to 660. Now we've heated it up to 660, we're going to do the latent heat bit. So the latent heat bit is mass times the latent heat. So it's 500 kilograms times 400,000 equals 2 million. No, it's going to be 200 million. So altogether, the total energy is going to be those two numbers. Added together. Add that to 288, which is a total of 488 million joules. Okay, so that's how much energy I need. So what are we doing? We're heating it up with this 87 kilowatts. So 87 kilowatts, that's 87,000 joules per second. And we've got an hour. So in 1 hour, we're going to get 87,000 joules times 60. That's how many would be in a minute. Times 60, that would be how many there is in an hour. So with an 87 kilowatt heater, I'm going to get that much energy. So that's how much energy is going to come from the heater. That's how much energy I need. So it's not enough. Not enough. Why would it take longer than the time calculated above? Why would it take longer to do that? Because not all the heat is transferred to the metal, to the aluminium. Some goes into the surroundings. There are other ways to do this question up here. There's lots of different ways to think about it, but that was one. You'd have the same answer though. Number 7, so we got the electromagnetic spectrum, put them in order. So the missing one here is going to be ultraviolet, and the missing one here is microwaves. One property that is common to all electromagnetic waves, they all travel the same speed in a vacuum. Or the other one you could have is that they are all transverse. Either of those will do. Visible light has been used to accurately measure blah 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 blah. Yeah, I may come back to that now. Let's have a look at the actual question. The diagram shows a ray of light entering a glass prism. The critical angle is 36, so anything that's bigger than 36, I'm going to have total internal reflection. Complete the diagram to show the path followed by the light. Okay, so just by looking at this, some maths, triangle is 180 degrees. If that's a right angle, that must be 45, which means that must be 45. And we always measure between the normal, don't we? Between the normal and the line. So it is this one we were on about. That's 45 too, which is bigger than 36. We're going to get total internal reflection. So it will reflect down here at an angle of 45, and then it will come out here at an angle of 45 as well. So I'll label those. And don't forget to draw your arrows. Explain why the ray of light would not be reflected back if it strikes the side of an angle of incidence of 30. Well, it would not be reflected back because 30 degrees is less than the critical angle. So not TIR. What will happen? It will refract. It'll go through the glass block and change direction, and it'll refract. Now we have a wavelength. Use equations. I can see is for 4 marks, so I'm going to need 2 equations. I'll probably use my first equation, find out something's missing, and then I'll need to get a second equation, find an answer, and bring it back to the first one. That's what's going to happen in this question. So what do we want to do? We want to use equations of page 2 to calculate the distance between the Earth and the Moon. And a light is the wavelength. So we want the distance there and back. Okay, so we also know here that the time is this. But that's the whole thing, look, to reflector and receive back. So the time just to go in one direction, one way, because that's what we're interested in finding out, is how far away the moon is. Just one way, that's going to be a time of 2.5626 divided by 2 seconds. Right, so we're going to use 2 equations. The first one we're going to do is speed equals, or the wave speed, equals frequency times wavelength. So we have a frequency using the numbers of 5.639 times 10 to the 14. Wavelength is 532 times 10 to the minus 9. That's going to give me a speed of 3 times 10 to the 8. Which I kind of knew anyway. That's the speed of light. Now I can use that equation to do my speed equals distance divided by time. I want to know the distance, so that's speed times time. I've just worked out my speed is 3 times 10 to the 8. But the time, remember, because I only want the time to the moon, is 2.5625 divided by 2. And if I put that into my calculator, I'm going to get an answer of about 7.7 times 10 to the 8 meters. That's my final answer. Could have gone straight to this, but if I remembered that the speed was 3 times 10 to the 8, go straight to that. Statewide, the laser light needs to be centered to the moon in pulses, separated by at least 0.57 instead of a continuous beam. Because if it was a continuous beam that was just going and coming back like that, then they're going to be overlapped, aren't they? They'll be meeting themselves on the way back, and we won't be able to detect a pulse. So so they don't interfere with each other. So words to that effect. That's a clue there, look. That's 1 second bigger, or 0.01 seconds longer than the time it takes to go there and back. So they go, come back, go, come back. Right, that's the 2017 paper. It was out of 80 marks in total. And for 2017, you needed 40 out of 80 for an A star. 32 out of 80 was enough for an A. 24 out of 80 was enough for a B. And that's the end of this paper. Ask me if you don't know or not sure of anything, or you just didn't follow, but hopefully we're getting better. Bye.